Hello, and welcome to this edition of the 2024 Von Karman series. I'm Nikki Wyrick from JPL's Communications and Education Directorate, and I will be your host for this discussion, how NASA's team of autonomous mini rovers will explore the moon. NASA's Cooperative Autonomous Distributed Robotic Exploration Technology Demonstration, better known as CADRE, is sending 3 small autonomous rovers, each about the size of a carry-on suitcase, and a base station as an experiment to map and explore the lunar surface. Joining us as co-host this evening is Sandy Marshall, Solar System Public Engagement Specialist at JPL. Hi, Sandy.
Hey, Nikki, thanks so much. It's great to be here. Remember, this is your space program, so we want you to be involved with this conversation. So if you're watching on YouTube, Facebook, X, or LinkedIn, ask questions in the chat box, and our social media team will bring in as many as we can in our talk tonight. And if you don't see the chat box, reload your page, and it should be right there. So thanks again, Nikki, and we'll hand it back to you.
Awesome. Thanks for being here, Sandy. So we will come back to you in a bit for those viewer questions, so please do keep those questions coming in. And a reminder tonight, if we run into any technical difficulties, we ask for your patience, and please stick with us. We'll get them sorted out as quickly as we can. Now on to tonight's discussion. Our first of 2 speakers for this discussion is Shubha Commander, CADRE Project Manager. Shubha brings over 20 years of engineering and leadership experience at JPL and in industry, and Shubha has worked on several incredible missions here at JPL, such as the Curiosity rover, Juno, and the Soil Moisture Active Passive mission. Hi, Shubha. Thanks for being here.
Hello. Thanks for having me here.
So, Shubha, let's jump right on in. What is CADRE?
CADRE is a mission to demonstrate a novel technology where we have a team of robots that will work together to accomplish a goal cooperatively without human intervention, so autonomously. We asked the question, we work so well as humans in teams, what if we extended that philosophy to robots? And CADRE answers that question. We're going to demonstrate this on the moon with 3 mini rovers. If you bring up image 1, you can see a picture of these from our clean room. And on the next slide, you can see they're about the size of a carry-on suitcase. So we have 3 of these mini rovers and a base station that we sent to the moon on a commercial lander provided by Intuitive Machines. You can see a picture of that on slide 6, if you can bring that up. And there's a CAD image of the lander provided by Intuitive Machines. And on the far right, you can see an inset photo of our rover and deployer, the actual flight hardware.
Thanks. So now we have an idea of what it's going to look like, but why is CADRE important?
Great question. So CADRE is a game-changing technology because it is going to revolutionize how we think about future exploration. Instead of sending one big rover, we can now send a team of robots, and they can be a mix of rovers and helicopters and hoppers all working together. This changes the way it opens up a whole new way of how we would do science. For example, you could put an instrument on each of these robots, and they can take a measurement at the same time, simultaneously, separated by a certain distance. So when you integrate the data from all of the instruments, you get a whole new layer of information. We're going to show an example of this technology in the next section when JP presents. This also gives us access to extreme environments like lava tubes and icy caves, because you could have a robot, you could potentially lose a robot, but still be able to collect the data from it because it would have shared that with the rest of the team. And it's also important to note what's unique about this technology is that each individual robot is an intelligent and smart agent. It can act and make decisions locally while still following the plan for the team. For example, if we're doing a formation drive, each robot can detect obstacles in its local immediate path and avoid it while still maintaining the formation with the rest of the team.
It sounds like this is a difficult environment. What are some of the challenges of building these small rovers for the lunar environment?
Yeah, so one of the first things that limits us is we have a very limited mass and volume to launch in each mission. And because we want to maximize the number of robots we can send in each mission for multi-agent autonomy like this one, each individual robot has to be really lightweight and small. So if you look at picture on slide 7, this is a family portrait of one of our early prototypes in front of the Curiosity testbed. So it's a totally different scale. And even though it's small, it still has to be very powerful to fit onboard sensors and the computing capabilities needed for autonomy to run. And once the rovers are on the surface of the moon, they have to navigate around the lunar terrain through rocks and craters and lighting conditions that are very different from the Earth. And they have to deal with dust. Lunar dust is very fine, and it can rise up and deposit on cameras. The rovers rely on images from their stereo cameras in order to navigate around obstacles. So if it's covered with dust, they can't see very well. So they have to do all of this autonomously, and they also have to deal with the extreme temperatures on the surface of the moon. To the equatorial region where we're going, it could be something from minus 100 degrees Celsius at lunar dawn or dusk to plus 100 degrees Celsius at lunar noon. So they have to field all of this on their own.
Those are some extreme challenges. And I love in that image that you just showed us, the scale between something like a rover the size of Perseverance and one of these CADRE rovers. How did you prepare the rovers for these extreme challenges?
That's the fun bit. We come up with innovative design solutions and analyze them to gain some confidence, and then we test them to show that they work. For example, to make them really lightweight and small, we turn to a lot of modern commercial off-the-shelf electronics and sensors, kind of like the processor you might find in your cell phone. If you look at image on slide 9, it shows a picture of how much we had to pack into this small volume. There's a lot of electronics and sensors there that are very powerful. You can also see we have both front and rear stereo cameras. So if the rover runs into iffy lighting conditions on one side, it can decide to drive backwards or do a wheelie and arc in place. To deal with things like lunar dust, for example, we designed the rovers such that there's no straight line path for dust to travel from the wheels and deposit on cameras or solar panels or actuators. And for the thermal environment, again, we have a very innovative solution where the rovers can predict based on the environment. They're responsive to their environment, so they can predict how much drive time they will have before they start to overheat. So as a team, they can decide, oh, we're going to overheat and let's go to sleep. They take a nap so they can cool off and radiate heat, and then wake up again as a team together and pick up where they left off. So they're really smart to be able to do that. And then we test the rovers. So if you go to slide 10, this is a video of our flight rover and our flight deployer being tested in our clean room as we anxiously make sure that it's able to egress out of what would be a lander and gently touch down on the surface. And it did that beautifully. So this showed that we would be able to successfully descend from the lander, egress off of it, and move away from the lander on the surface of the moon. And on the next slide, we then subjected them to some vibration testing, kind of the environment they would see during launch, and made sure that they could withstand that. And on the next slide, let it finish. This is where we put the rovers into a thermal vacuum chamber and expose them to the temperatures they will see on the surface, and again, make sure that they can survive those temperatures. And I'm happy to report that the rovers all passed these tests successfully with flying colors, so they're ready for flight. And on slide 8, if we can go back, we have these stunt doubles for our rovers. Essentially, we can take these other stunt double testbed rovers out of the clean room into our Mars yard at JPL, where we can test these rovers with actual terrain, rocks, craters, We even do some nighttime testing with floodlights and spotlights to simulate the lighting and shadow conditions these rovers might see to verify their autonomous navigation capabilities.
I mean, you've shown us some great pictures of your testing, and I would love to highlight as well the people in all of those images, right? This is not just about a team of robots that's doing this incredible work, but also a team of people.
Absolutely. It takes a remarkable team of humans to put together an amazing team of robots. And I'm very fortunate to have a team of very creative and passionate people who are very determined to put all of this together, and their families who have, if you're watching, thank you for supporting the team and our dedication here. I have a picture here of our team on slide 13. This is the team in the Mars yard with the prototype rovers in front. And then on slide 14, we have a picture of a subset of the team in the clean room with the flight rovers in the front, and you can see the solar panels here opened. We've also had a lot of support from JPL and NASA for a lot of people who have helped make this possible and who've been very invested in our success. And I want to add that a team like pulling a mission like this together, it takes all kinds of people and all types of people. So we have a very diverse team with a lot of different backgrounds, education, experiences. And so if something like this really sparks your interest, I would say follow that passion, because there's always a place for you, a role for you in space.
And speaking of what the future holds, not just for our audience, but what does the future hold for this technology?
Nikki, it's such an exciting time for lunar exploration right now in the industry, and we are very keen to make this autonomy technology available for the public, for industries and universities to be able to infuse into their missions. We're also looking to, we're already feeding forward some of this autonomy technology and the off-the-shelf power and avionics systems into our next mission concepts like Endurance, which is a long-range lunar rover study, and our larger projects like Mars Sample Return. And I want to emphasize this is not just about teaming within robots. As we become more of a spacefaring civilization and we start to set up a moon base and send more humans out into space, robots can work with astronauts, especially for the sort of repetitive, fatiguing, riskier tasks where, like, multi-robot construction or mapping unexplored areas or scouting for minerals and water or traversing very large distances to collect samples. And those are the sort of things that robots can take care of that frees up the astronauts to do the tasks that only they can do. So it's a very exciting time, and I think this technology has a lot of possibilities. And there's a graphic on slide 15 that shows that there's applications of this technology on the Earth, the Moon, and beyond. It can be exported to all other explorations as well.
Really paving the path for the future, Shubha. So I know the audience has asked a ton of questions so far. So Sandy, what are they asking out there for Shubha?
Yeah, thanks, Nikki. And big thanks to everybody in the audience for asking some fantastic questions and the great engagement we're seeing all across the platforms. Shubha, we got a few questions here for you. The first is from That Opal Guy on YouTube, who asks, what process was used when designing the wheels for these rovers?
That's a large question. I think the main thing we wanted to look at was lightweight materials, because our big constraint is mass. And we wanted to, again, make sure that there's no ballistic path of dust from the wheels, so that it doesn't kick up a lot of dust that can get deposited on solar panels and such. And we wanted it to be something that's easy to manufacture and install, and still be able to climb over rocks and such. In one of our demonstrations in the Mars yard, the rovers have shown to be really capable, where they almost climbed a rock that's about the size of the rover itself. So those are the sort of factors that go in.
Thanks so much, Shubha. That's excellent. The next one's about exploration. And Inga on Facebook is wondering, can these be used to explore moon caves or lava tubes?
Absolutely. I think this gives us extra access to these sort of extreme environments because as a team, these robots are collecting data and sharing the data amongst themselves. So even if we lose a robot, the team can plan around that. And the rover that we lost would have already shared its data with the rest of the team, so we would still be able to get that. So this autonomy technology can be applied for extreme environments like that.
Well, and in speaking of other applications, Pia on LinkedIn is wondering, will autonomous helicopters be deployed?
That's, again, one of the possibilities of this technology. We could even have a team that's a mix of a rover and a helicopter and a hopper. The technology itself, the autonomy stack, the software stack, is independent of the underlying platform, the hardware platform.
Well, thanks so much. Well, thanks again to the audience members across all the platforms for the great engagement. Please keep those questions coming. Shubha, thanks so much for those great insights. And Nikki, we'll hand it back to you.
Great, Sandy. Thank you so much. And Shubha, we will be coming back to you a little bit later for some joint Q&A. But now I'd like to introduce our second speaker for this discussion, Dr. Jean-Pierre Delacroix, CADRE Principal Investigator. Jean-Pierre, or JP, earned his PhD in electrical and computer engineering with his research focused on new control techniques for large-scale robotic systems. At JPL, he continues to work on multi-agent robotics for new and challenging applications, such as the CADRE technology demonstration. Hi, JP.
Hi, and good evening.
So tell us a little bit more about the autonomy of these robots.
Yeah, absolutely. I think we can take a look at slide 16, where we've got some of our prototype rovers operating in the Mars yard at JPL. And the test that they're doing in this image is all about maintaining a even spacing as they drive through the Mars yard and try to avoid rocks. And really, autonomy makes this happen, but it really makes this happen at two different layers. There is one layer that I will call maybe like the surface mobility layer, where the robots, because they have all of the sensing, they have the cameras, they have the inertial measurement units, they've got sun sensors, they can basically track their motion through the world. They can understand what the world looks like, and they can drive themselves from point A to point B. So they're individually quite capable. And one could say, well, why wouldn't you just tell each individual robot where to go from the ground? But it makes it very difficult for them then to stay coordinated, right? Because they might go out of sync because they're not working together as a team. So the additional layer that we really need and that we're demonstrating with CADRE is what we call multi-agent autonomy. And this is the layer that brings a bunch of autonomous robots together and makes them work as a coordinated team. So this layer basically thinks about, well, if I have 2 robots or 3 or maybe even more robots, how would I arrange them? How would I ask them to drive together so that they always stay in equal spacing? How do I make sure that the team avoids all of the rocks and the craters and successfully completes their task?
Yeah.
So that's what we're looking at here.
Let's bring up graphic 17, JP. What are we seeing here? I think that helps explain a little bit what you're talking about.
Yeah, absolutely. And there's an interesting thing that the team does, which is actually called leader election. So rather than the robots arguing about, how do we get this task done, what they make an initial decision to say, okay, this robot is going to be our team leader for this portion of the mission. And then the team leader basically asks all of the other robots, okay, give me all the information that you have about the lunar surface. Let's combine our knowledge and figure out what the lunar surface looks like. And then the leader plans for the team. And once the leader has planned for the team, it provides each one of the members of the team with a kind of a plan to follow along. And then they communicate with each other about how that plan is progressing. If anything happens that they didn't expect, they communicate with each other and they stop and then they replan and they try again. And they kind of keep doing this until they're successful.
I love that teamwork. So let's pull up graphic 18. I think that's another good example of this teamwork you're talking about.
Yeah, and this specifically gives you an idea of how the robots, first of all, see the world, right? So they each see their own portion of the lunar surface, for example. And in this specific case, it's actually part of our clean room, which is why it's nice and rectangular. But you can see that rover 1, 2, and 3 each have kind of a piece of the map, right? But to do a better job of planning, what's the best thing to do is for them to each send that information to a leader, and then together they actually have a complete view of what the entire environment looks like, and they can do a much better job of planning their work in that space.
Sounds like an incredible group of robots. So what is a day in the life of CADRE? How does this team operate and sort of make those decisions?
Yeah, we can look at slide 20 for that. Here's an interesting plot of basically what it would look like for the team to work together. This shows you basically at the top that really you can think of the activities that they do in really three parts. They tend to drive to achieve an objective because they're robots. They move around. They do something called downlink or just communication, right? They talk to each other. They have to exchange that information, as we saw, to understand the world, and also tell us, on the ground what they saw. We want to know what they're seeing. And then they also, interestingly, spend some time sleeping. And that's because we have a constraint or two constraints at play here. One is the state of the charge of the robot. So they have a battery and they have to recharge their batteries using solar power. So sometimes they have to go and sleep and recharge those batteries and energize again for the next round of activities. And also temperature matters. So every time that they move and think, they're basically heating up a little bit more. And there's a maximum temperature that they can tolerate. So again, going to sleep helps them kind of cool off and relax a little bit before they're asked to go and do some more work.
These robots, they're not just changing the way we explore, right, JP, but they're also changing the way we can do all of the science?
Yeah, absolutely. And we can maybe take a quick look at the video in 21, just for a little bit of background. But I'll say that CADRE specifically is designed to demonstrate multi-agent autonomy. So it is all about the autonomy. But we also wanted to show that it's not just autonomy for autonomy's sake, but that we are proving a technology that has the opportunity to kind of transform the way that we do science in new ways. And specifically in this example, what we're showing is something called a multi-static ground-penetrating radar survey. So it's a radar that's pointed into the ground and allows the robots to work together to see what's in the ground. And if we look at image 24, then we can, for example, here see an example of what we do today. So today we have a single rover with a single ground-penetrating radar. And again, CADRE is the idea of, well, what do you actually gain from having multiple ground-penetrating radars that work together? What does them being coordinated gain you in terms of the science data that you're able to collect? So if we look at slide 25, again, in the case where we're today, we do something called single monostatic measurement. So we have the singular ground-penetrating radar, and you can imagine a robot driving through the environment and just collecting data from this radar. And it would integrate this data measurement by measurement as it's driving along, because it's keeping track of where it's driving. And what you can do is you can get a two-dimensional slice of what the subsurface looks like. And this is really limited by the fact that our robots actually are not perfect at estimating where they are. So over time they kind of drift, and the measurement kind of loses on its quality. So if we look at slide 26, though, with CADRE, if you use multiple ground-penetrating radar, you first of all drive much shorter distances individually between the robots. So first of all, drift doesn't impact the robots as much, and it doesn't impact your measurement as much. And that's because each robot drives the shorter distance, and it's integrating for shorter amounts of a shorter amount of measurements effectively. But what's really key here is that when the robots are a certain distance apart from each other and they're sounding, they're also able to hear the radar signals from the other members on the team. And by integrating that additional piece of data, which you're unable to do with a single robot and a single ground penetrating radar, you're actually able to do a 3D reconstruction of what's in the subsurface. So it's giving us a completely new way to look at what's in the ground and not just on the surface of the moon.
JP, how do you go about testing the capabilities of the rover's autonomy?
Yeah, we do a lot of testing. If we look at slide 27, some of our testing happens on the flight hardware. So those are the actual robots that are going to the moon, and here we're testing it. And by the way, the tall person in the middle there is me in what we call like a bunny suit to keep the robots clean and safe. But you can see in this environment, we're testing with the actual hardware that's going to go to the moon and the software that we've developed that's going to be making these robots autonomous on the moon. But our ability to really test all facets of the autonomy is a little bit limited in the clean room, right? Because we can't dig craters into our floors and not really bring in any sort of rock. So we have this simplified environment, but it really helps you to at least functionally validate that everything works, right? You can see that the software is correctly collecting data from the cameras, that they're generating basically images and then point clouds and maps of the environment, that they're able to track their motion and that they're able to communicate with each other. So all of the important functionalities are validated in this space. And then what we do is we take in slide 20, well, before I jump to that, let's actually look at slide 28 because it's a video of the rovers driving in the clean room at JPL. And you can see 3 of them are doing this coordinated drive that I mentioned earlier. And I think what's really neat here is twofold. First of all, you're seeing video images live from all 3 robots, so you can kind of see what their perspective, what their world looks like. It looks quite a bit different from us. The cameras are much lower to the ground, and they can see less far ahead, and they have a little bit a lower field of view. And then in the bottom half of the screen, what you're seeing is their understanding of what the world looks like, right? It's not in necessarily at the end of the day when they're doing that planning. They're not planning in these images, but what they're doing is they've taken those images and kind of labeled the world as, hey, these parts of the world are safe for me. These parts of the world are not safe because they're either rocks or they're craters. But yeah, then they successfully plan together and drive together and achieve their task. So now moving into the other test venue on slide 29, we have a video of basically this exact same capability. But what we're testing here is more about the performance, right? So we know functionally it works, but we can take our development rovers, which are not going to the moon, but are kind of the stunt robots, or they're designed to operate in this environment, to be able for us to go out there and test on a regular basis. And then now you can incorporate more parts of the environment, right? That we have these sandy surfaces, we have rocks, we can dig craters, we can have different lighting conditions by either testing during the day when there's sunshine, or we can go out at night and point spotlights and create these like really dramatic shadows that you would also see on the moon. So it allows us to really fully test the system in varying different environments and scenarios.
How did a mission like CADRE come to be, JP?
Yeah, that's also a fantastic question. So if we want to go to the beginning, let's look at slide 30. So what you'll notice there is that it began roughly around 2015, and it started all with a NASA SDMD game-changing development program project called Puffer, which is Pop-Up Flat Folding Explorer Robot. And really the point of that project was to think about whether you can develop a robotic platform with very unique mobility capabilities, meaning it's very highly capable and can solve things like going underneath overhangs and going up steep slopes, and also keep that mass and volume really, really low and small, right? So showing that you can be tiny but mighty, if you will. And what that really also showed is that because we're typically constrained on mass and volume, is that now you have the ability to maybe bring 2, 3, 5, 10 robots with you because you've built them small, but you've retained their ability to do the things that we want to do with them. So that brought about a second GCD task, which was called autonomous buffer. So that's on the next slide. And here, what we did is that we said, okay, we now have hardware that's capable. We can add some more sensing that's now specific to the autonomy. Let's give these rovers some more, cameras, for example, which we tend to rely on. Let's also work out, radio so that they can communicate with each other. So add a little bit more hardware capability on the sensing, on the compute, and the communication side, and then start adding this multi-agent autonomy, right? So we demonstrated that they can explore together cooperatively. You can throw them into an environment that they've not previously mapped, where we have no idea what the environment looks like, and they can successfully map out this entire environment and send us back a map. And that's what we proved under autonomous puffer. And then this was still a what I would call like a research project, right? We were really figuring out how could this work. How could we make the hardware and the software and the autonomy all work together to build a system that can do this. So, well, once we've proved that, we were ready kind of for the next step. And then we had a third GCD project, which is CADRE. So that's on the next slide. And CADRE really is taking the technology that we've been developing for quite some time in both terms, the hardware, the software, and the autonomy, and really turning that into a flight system, right? So you're further stressing kind of all of the things that you have to think about when you're sending something into space. And then also what we did is we added the multi-static ground penetrating radar that we talked about earlier.
This is all great information, but I know the audience has asked so many questions. So Sandy, what are they asking out there for JP?
Well, Nikki, we have a lot of fantastic questions from the audience for JP. Actually, one specifically for JP from Corey on LinkedIn, who's wondering, do they use electric and or magnetic fields to reject dust that could have static charge that may attract it to the robot?
I don't believe we have any technology that actively does that.
Okay, so excellent. Bob Fillmore on YouTube, we're moving over to YouTube now, is wondering, there isn't anything like GPS satellites at the moon yet, so how do the rovers navigate?
Yeah, that's a fantastic question. Indeed, we don't have the luxury of GPS as we would have here on Earth. So the robots do this, again, in kind of two layers. So first of all, they rely on their own ability to track features in the environment through the cameras. We have front and rear facing cameras on the robot, so they can track the features, and by measuring how those features move image to image, they're able to basically perceive their motion through the environment. And then they start layering out in other sensors. So we also have an inertial measurement unit. So an inertial measurement unit typically has a accelerometer, it has a gyroscope, and then it also has a compass. So the accelerometer and the gyroscope is additional information that we use to measure the robots use to measure their own motion, and they kind of correlate that with the feature tracks in the image. The compass is interesting also because the compass we can use here on Earth, but not as much on the moon. So we instead use a sun sensor. So the robots are estimating the location of the sun, and because they can basically figure out where is the sun in the sky and what time of the day it is, they can back out what is their orientation on the moon. So those three things together allow them to track their motion. But then they also do something as a team. So in addition, each of the robots has something called a ultra-wideband ranging radio. And it's basically a radio that they can use to measure the distance between each other. It uses time of flight, and by just measuring time of flight, you can basically estimate the distances between robots. So it gives the robots an additional piece of information, knowing that, hey, I think I'm a robot and I think I'm here, and I have a buddy that's over on the other side that also thinks that they're in their spot. Let's also verify that using that inter-robot ranging measurement. And by doing that all together, they can basically help each other localized as well. So they work as a team to manage without GPS.
Well, that's excellent. Thanks for going into that detail, by the way. There's a number of questions about information sharing between the rovers and how that works. So thank you so much for covering all those bases. Another question, this one is from X, and this is from Randy on X, who's asking, what will these rovers do that hasn't been done before?
So it's for us, it's really about having a coordinated team of robots. Again, mostly we send single robots out on missions, but in this case, we're sending a team. And again, what we're trying to show is that you can use multiple robots to, first of all, explore the surface of another planetary body other than Earth. All right, so that's why we're going to the moon. And we're showing that they can work together and show us what the surface looks like in higher detail than we're able to even see from orbit. And then second of all, again, going back to the ground penetrating radar, is that they can do what we call a class of measurements called distributed measurements, right? We have instruments in different places taking measurements at the same time and correlating that data to learn something that you just simply can't do if you were to have a single robot drive to all 3 of these points, but separated in time. So you're taking advantage of the fact that you've got 3 or more of them in the environment.
That's excellent, JP. Thanks so much for helping to answer those fantastic questions. And we have so many and a little bit of time. So Shuba, we're going to bring you back in as well. And we got a couple of questions, a few actually, for both of you. So we'll kind of do a tag team. And if one of you would like to jump in as well, please feel free. Shuba, we'll start with you on this one. This is from FatMat426 on X, who's wondering, will the rovers be protected from dust accumulation? And also, how will they cope with the temperature variations?
Yeah, so we have, for sensitive parts like actuators, we have filters and seals. The electronics inside are also conformally coated so to prevent dust from getting in there. So they do have certain protection barriers from dust. In terms of the temperature, we're using a lot of commercial parts, off-the-shelf parts, so we find ways to radiate heat if necessary, or add heaters where we have to keep them warm enough. So we have a combination of heaters where needed and radiators. That's why our solar panels actually deploy so that we're not covering the radiator. We're exposing as much of a radiator space as we can so that they can radiate heat out and keep the rover cool enough.
Well, thanks so much. And that's a great transition to our next question, actually. JP, this one's for you. This is from Thanos on YouTube, who's wondering, another question about solar power, actually. It's a good transition. Is solar power easier on the moon than it is on Earth?
Well, that's a great question. I don't think I've really thought about that deeply or done the analysis to say so. I mean, I will say that because we're going to the equatorial region, we have the ability that throughout the day, we'll have the sun practically overhead. It won't be kind of low on the horizon all the time, and that makes it easier for our solar panels, which are facing upward, to collect solar power throughout the mission. And then the only other thing I can really think of is that we don't have clouds on the moon to worry about. What we do know is that we've done the modeling to know that the robots have the ability to kind of sustain themselves off of the solar panel. And I think I also earlier talked about the autonomy itself is reasoning about the state of charge and making sure that the robots don't go longer than they have charge for, so that they always kind of end their work early enough to go and sleep and take enough time to recover enough energy for the next work session.
That's excellent. Thank you so much. Okay, Shuba, we're going to move to you. We've had a couple questions about solar power. We're going to move to software. So we have a number of questions about the software on the project. If you could share, this is from Payman on LinkedIn, who's wondering if you could please share with us what software package you use for the mission simulation.
We have a in-house JPL simulation tool called DARTS, which actually uses images from LRO, the Lunar Reconnaissance Orbiter, as well. And so that's one of the tools that we use for simulation. I don't know, JP, do you have anything else to add?
No, that's correct. I would also say that in our earlier prototyping phase, when we needed some simpler simulation, we used Gazebo and ROS, which is the robotic operating system. So those are both open source tools that you can get access to. So we used that earlier in our development, in addition to Darts.
Thank you so much. So Darts, Gazebo, and what was the third one?
Gazebo is usually part of the ROS, which is the robotic operating system. So those two things go together. Yeah.
Excellent. Okay, wonderful. So the next question, JP, we'll stick with you on this one. This is from Terry on LinkedIn, who's wondering, what's the expected duration of the mission and what area is going to be covered by this team of autonomous rovers?
Yeah, we're expecting to operate for a single lunar day, and the kind of the operational area that we have for this technology demonstration is within 100 meters radius of the lander. So we're going to have the robot stay within that area, and then each one of the experiments that we're doing, in both in terms of the exploration and the distributed measurement, they can range anywhere from 5 meters squared or 5 meters of driving all the way up to 20. So those are roughly the kind of the envelope of our experiments that we'll be doing with the robots.
That's excellent. Thank you. Shuba, this next one is for you. This is from Sue on X, who's wondering, big picture, what is the most valuable information you expect to collect with the rovers on the moon?
In this particular mission, again, this is a technology demonstration. We don't have science requirements, but our main goal is to prove the feasibility of a cooperative, autonomous distributed measurement. So if we are successful with this, it can scale to larger rovers, to, like we said, a combination of rovers and other platforms, other vehicles. So it's mainly a proof of concept that this cooperative autonomy technology can work outside the Earth. And as part of that, we also have this ground penetrating radar demonstration, and being able to show that we can map 3D subsurface maps. It would be a great proof of concept.
That's excellent. Thank you. So JP, we'll go to you for this next one, and then to Shuba for any other thoughts. This is from General Turian on YouTube, who's wondering, are there plans in the future to use this same approach as CADRE on other locations, such as Mars, Titan, etc.?
Yeah, absolutely. I think, again, our hope with this technology demonstration is really that it's going to spawn follow-on missions that will take advantage of the technology, right? You could certainly see different instruments and different locations being combined with CADRE and being successful in those places that were mentioned.
Thanks. And Shuba, we'll hand it to you for any other thoughts on plans for the future to use the same approach as CADRE on any other locations.
Yeah, absolutely. Once we show this on the moon, I think it's really a precursor to being able to show this anywhere else in the solar system, including around Earth. And I talked about extreme environments earlier, so there is a lot of extreme environments in other places too. I don't see why this couldn't be extended to ocean worlds or icy caves or other forms of robots. The autonomy software could be ported onto those vehicles as well.
That's excellent. Well, Shuba and JP, thank you so much for those answers and perspectives. And again, thanks to the audience for these fantastic questions. And Nikki, we'll hand it back to you. Thanks so much.
Great. Unfortunately, that's all the time we have today for audience Q&A. But Shuba and JP, I did wanted to throw it to you for one final question that I know is very important to both of you, which is, what advice do you have for folks in the future? You're talking about the future of this mission. It's a technology demonstration. We're laying the groundwork. We always say this is your space program to our audience and our viewers. So what advice do you have for aspiring scientists, engineers, folks who wanted to get into this field?
Yeah, I guess I'll go first. We always say, follow your passion. What does that mean exactly? I think to me, it means two things. One, curiosity, asking the big questions of how does this work? How can I make it better? And then putting in that dedicated effort and persevering through challenges. So, and taking care of people along the way. So it really boils down to curiosity and perseverance. And one of the things that I really love about this job is it lets me keep my natural sense of wonder and awe about this universe. There's just so much we still have to learn about the universe and our place in it. So it can be very enriching and humbling in many ways.
And JP, how about for you?
Yeah, I mean, well, first of all, I fully agree with what Shiba said, and what I would add to that is that just know that whatever you may be interested in and what you're passionate about, there's a place for that, and it's required to make things like CADRE happen. Like our robotics and space missions and all the things around it really require a very large team with a very diverse set of experiences and expertise. So as long as you, again, follow your passion, follow through with that, you will find your place, and you will be successful, and you will end up contributing to something like this as well.
An amazing mission, an amazing discussion. Thank you both. Folks that are watching, remember, if you want to find out more about CADRE, please visit the link on the bottom of your screen now, go.nasa.gov/CADRE. I want to thank our speakers, Dr. Jean-Pierre Delacroix. I want to thank Shubha Commander for joining us to chat about CADRE. Also, thank you to our Wonderful Questions co-host, Sandy Marshall, and all of the folks working behind the scenes to make this possible. To all of you watching, thank you for taking the time to join us every month. And if you've missed any of our Von Karman series from the past, please check out JPL's YouTube page. Join us next month for a discussion on the Near-Earth Object Surveyor mission with Mark. Thanks again, and we will see you all in August. Bye.